right, Assalamu alaikum. Now I'm going to talk about special types of matrices. In particular, I'm going to talk about diagonal matrices, triangular matrices, and symmetric matrices. Throughout this semester, we're going to talk about special types of matrices, and those in particular, they are nice, easy, and we are going to use them a lot. They have some nice properties. It is like when you talk about functions and you say even and odd functions, or you say continuous functions, or you say increasing functions, or you try to divide your huge family into subfamilies, and those subfamilies, they have certain nice characteristics that you can talk about. So what do we mean by diagonal matrix? Well, as the name suggests here, diagonal it means your matrix. Here is the diagonal. This is what we call the diagonal. You have something here, and here you have zeros. If your matrix is of this type, we say the matrix is diagonal. Okay? So along the diagonal, you have something, whatever it is, but for sure, here and here, you have zeros. For example, if I give you this matrix, 1, 0, 0, 0, 5, 0, 0, 0, negative 7, right away you say, well, this is a diagonal matrix. The identity matrix is a diagonal matrix. Okay? What about the zero matrix? Let's say 3 by 3. Is this a diagonal matrix? Yes, it is. Look here, I said something. I don't care what you have along the diagonal. It could be zeros or it could be non-zeros. Okay? So as long as you have zeros here, it doesn't matter what you have here. Okay? So this still belongs to the diagonal family. Okay? So diagonal matrices, they are very nice, easy matrices to deal with. Okay? If you have a diagonal matrix D in general, D equals, let's say A11, A22, A33, ANN, and zeros here, zeros here. Right away, you can think about D exponent K for any positive integer K. So if K here is 10 or 100 or a million, it doesn't matter. This is going to be here A11 exponent K, A22 exponent K, ANN exponent K. Why is that? Well, you can multiply and see. What happens if you multiply D by itself? Do the multiplication and see. You are going to find you get the elements along the diagonal raised to the same exponent. Okay? So that is very easy to verify. So from now on, if you have a diagonal matrix and you want to find, or you want to raise it to a certain exponent, you just raise the elements along the diagonal to that exponent, and that's it. Okay. What about the inverse of a diagonal matrix? So let's think about 2 by 2 matrix. A11, 0, 0, A22. So this is your matrix D. Or let me call it D2 because it's 2 by 2. Well, if you use the formula for a 2 by 2 matrix, right away you can see here D2 inverse is going to be what? It is this times this minus this. So you have A11 over A11 A22. No. You have A22 over A11 A22. And here you have 0, here you have 0, and here you have A11 over A11 A22. So what is this? Cancel A2 with A2. Well, first, A11 A22 has to be non-zero. So this should be non-zero, this should be non-zero. In that case, what do you get? You get 1 over A11, 1 over A22. Correct? Provided that A11 is not 0, A22 is not 0. So now can we generalize this? Well, that suggests something here. If you want to think about the inverse of a diagonal matrix, first, you need those elements along the diagonal to be non-zero. Number two, if you want to write the inverse, you take the reciprocals of those numbers. So for this D, you can say here D inverse is 1 over A11, 0, 0, 0, here 0, here 1 over A22, 0, 0, 0, 0, 1 over A33, here 0, 0, and you keep going in the same way. At the end, 1 over ANN. Okay? Well, if you are not convinced about it, all you need is to multiply this by this. Multiply this by this, what do you get? Here, do it. You get 1. So if you multiply D by D inverse, you are going to get the identity. Okay? So for diagonal matrices, it is very easy to see whether they are invertible or not just by looking at those elements. You need none of them to be 0. Okay? And if that condition is satisfied, right away you can write the inverse. Okay? You don't need to do much work right away. This is about diagonal matrices. Okay? Now, if you multiply 2 diagonal matrices, what do you get? You get a diagonal matrix, correct? Think about multiplying 2 matrices of this type. Do the multiplication. What do you get? Still you get a diagonal matrix. Okay? Let me say the following statement and tell me whether it is true or not. Diagonal matrices commute. I mean by that, if you have a diagonal matrix D1 and you multiply it by diagonal matrix D2, that will be the same as if you multiply D2 by D1. True or false? It is true. Do it. Do the multiplication. In general, do the multiplication. If you have this one and you have another diagonal matrix that is B11, B22, and do the multiplication right away, you see it is commutative. Okay? You know, some people like to write diagonal matrices instead of like this. They write them D equals diagonal like this. A11, A22, ANN. It is kind of convenient just to write it like this. It means those elements are coming along the diagonal, and elsewhere you have zeros. So if you go to the library and you open a book and you find this, don't be surprised. This is what we have here. All right, so this is about diagonal matrices. What about triangular matrices? Triangular matrices. Triangular matrices, here is a square matrix, here is this part of the matrix, and here you have whatever. And here you have zeros. Or it could be, here you have whatever, and here zeros. You see here? This is upper triangular, this is lower triangular. Upper. triangular. This is lower triangular. Upper triangular, lower triangular. Okay? Again here, I'm saying whatever. So it is possible that you have zeros, or it's possible you have something else. It doesn't matter. Okay? So, for example, if I give you a matrix like this one, is this upper triangular or lower triangular? Or, well, for sure here, this is diagonal. But can we say this is upper triangular? Yes, we can. Can we say this is lower triangular? Yes, we can. So a diagonal matrix is both upper triangular and lower triangular. Okay? Here is another example. This matrix 1, 2, 3, 0, 4, 5, 0, 0, 6. This matrix is upper triangular. This matrix A, B, 1, 2, 3, 4, 5, here 6, here 0, 0, 0 is lower triangular. Okay? So you already observed when you get echelon form, in echelon form, it is upper triangular. While doing elementary operations, it is what you get in the echelon form, or what you get in an echelon form, is upper triangular. Okay? You can observe that the transpose of an upper triangular is a lower triangular. The transpose of an upper triangular matrix is a lower triangular. And the other way around is true. The transpose of a lower triangular matrix is an upper triangular matrix. Remember, the transpose, you make the rows columns, correct? So this upper triangular becomes lower triangular. Okay? Can you think about the product of two lower triangular matrices? The product of two lower triangular matrices. Of course, they have to be of the same size, so you can multiply. Okay? The product of two lower triangular matrices is a lower triangular matrix. Write two triangular matrices, two lower triangular, and multiply. Look, when you multiply, what do you get? You get a lower triangular matrices. Similarly, if you do the product of two upper triangular matrices, it is going to be an upper triangular matrix. So the same thing here, same for upper triangular matrices. Okay? So we know the meaning of a triangular, upper triangular, lower triangular, and we know what happens to the transpose. We know what happens when we multiply two upper triangular or two lower triangular matrices. About the inverse, or talking about the inverse, well, you need more ideas before you make a conclusion. But we'll talk about it later on. All right, now let's talk about this. This is interesting here, symmetric matrices. symmetric matrices. A matrix A is called symmetric. What does it suggest? If A transpose is the same as A. Symmetric. So what you have on this side is what you have on this side. Here's an example. A equals 1, 2, 3, 1, 2, 3, 4, 5, 5, here's 17. This is symmetric, correct? You take the transpose, you get the same matrix. A transpose is the same as A. Okay? Such this matrix, we call it a symmetric matrix. Let me ask you this question. Is it possible for a symmetric matrix to be triangular? Or if a symmetric matrix is triangular, what does that mean? Or if a triangular matrix is symmetric, what does that mean? Let me help you by rephrasing my statement. If a symmetric matrix is triangular, then it must be diagonal. True or false? If a symmetric matrix is triangular, then it must be diagonal. Yes, that is a true statement. Look, I'm connecting here the three concepts together. If a symmetric matrix is triangular, then it must be diagonal. If a triangular matrix is symmetric, then it must be diagonal. I'm just here playing with words, okay? All right. Let us take any square matrix. Let us take any square matrix, n by n matrix. Number one, what can you say about A plus A transpose? A plus A transpose. What can you say about that? Well, let's call this B. Look, what happens if I take P transpose? That is going to be A plus A transpose, all transpose. Now, from the previous properties, this is going to be A transpose plus A transpose transpose. The transpose of the transpose, that is A. So this is A transpose plus A. And that is the same as A plus A transpose. So that is the same as B. So what can you say here about this? We can say A plus A transpose is symmetric. So for any square matrix, if you add A to A transpose, you get a symmetric matrix right away. Okay? All right. There is something called skew-symmetric. Skew-symmetric. A matrix A is called skew-symmetric. Skew-symmetric. If A transpose is the same as negative A. Think about it. A matrix is called skew-symmetric if when you take the transpose, you get not A, you get negative A. Can you think about an example here? Here is an example. A equals 0, 1, negative 1, 0. Very simple. What is the transpose of this? 0, 1, negative 1, 0. And what is this? This is negative A. Correct? Now, this is a very simple example. You can observe that I'm putting zeros along the diagonal. Is this just a choice, or is it a must? I mean, if you want to talk about skew-symmetric matrices, does it mean along the diagonal you must have zeros? Think about it. You want this to be this. Remember, when you take the transpose, the elements along the diagonal, they stay unchanged, correct? So if you want this to be the same as this, so you need whatever you have here to be the same as the negative of this. So you have no choice but to make it 0. So if you are talking about skew-symmetric matrices, you must have zeros along the diagonal. Okay? All right. Now let me go back here. I have an n by n square matrix. What can you say? What can you say about A plus or A minus A transpose? So you have a matrix A. I'm going to take the transpose of A, and I'm going to write A minus A transpose. I'm going to call this B. What can you say about this? Here I ask you, what can you say about this? Now I'm asking you, what can you say about this? Well, let's see here. B transpose is going to be A minus A transpose, all transpose. And that is going to be A transpose minus A. And that is going to be negative A minus A transpose. And that is negative B. So B transpose is negative B. Correct? So if you subtract here the transpose of A from A, what do you get? We get a skew-symmetric matrix. Hence, we get, or what can you say? We get a skew-symmetric matrix. So here, if I ask you to give me an example of a skew-symmetric matrix, just take any square matrix, take its transpose, and subtract the transpose from A, you are going to get for sure a skew-symmetric matrix. Okay? Symmetric matrices, skew-symmetric matrices. All right. True or false? The identity is a symmetric matrix. It is true. The identity is a skew-symmetric matrix. That is false. It cannot be. Remember, you need zeros along the diagonal. All right. If A and B are n by n symmetric matrices, what can you say? What can you say about AB? A and B are two n by n symmetric matrices. What can we say about AB? Well, let's see here. AB, if I take the transpose of that, it will be B transpose. Remember the properties that we discussed before? So this is this. Now, B is symmetric, so that is going to be BA. And A is symmetric, so that is A, so BA. So this is going to be this. AB transpose equals BA. So what can you say here? Well, you can say AB is symmetric if they commute, AB, BA, if AB is the same as BA. So the product is symmetric only if the two matrices commute. The product of two symmetric matrices is symmetric if they commute. Look, we can ask you like a fancy question, but the answer is very easy. I can say, or I can ask you, let A and B be two n by n symmetric matrices. Show that AB is symmetric if A and B commute. Well, it looks like a fancy question, but actually it's very simple. Here it is. Here's the answer. Okay? All right. Another question. Again, if you think about it, it looks fancy, but it's very simple. If A is invertible and symmetric, what can you say? What can you say about A inverse? It is invertible, so A inverse exists. A is invertible and symmetric. What can you say about A inverse? We can say A inverse is symmetric. Why? Can you prove that? Again, the question here looks fancy, but it's very simple. Here's the proof. I want to show that A inverse is symmetric. What does that mean? It means if I take A inverse and I take the transpose, I should here at the end get what? Get A inverse. Well, using the properties that we discussed before, this is going to be A transpose, here inverse. Now, A is symmetric. Here, we are saying A is symmetric. So, A is symmetric. So this means you are going to get A, and here is the inverse. Well, but that is what we want. That's it, done. Okay, look how simple is that. All you need here is to master those concepts and just digest them. Once you digest them, then you can do a lot of gymnastics here, and you can come up with fancy statements that you can see somewhere either in the text or in the exams. Okay? All right. Basically, that's all here. That's all about diagonal, triangular, and symmetric matrices. Later on, we are going to discuss some other properties, but for the time being, what I gave you here about diagonal, triangular, and symmetric matrices is good enough. All right, that is a very short section. Thank you very much, guys, and please do your homework, okay?